Welcome to another great video. So this is another past paper example. In this particular example, we were focusing on November 2018, right? So it was question 8 on that paper, electrostatics. So we are given this particular problem. Okay. So we are told that two identical point charges, X and Y, are placed 2 millimeters apart. Okay, let's start there. If we are told that they are identical charges, it means if charge X is 2 coulombs, charge Y also has to be 2 coulombs, right? If charge X is positive, for instance, charge Y also has to be positive. So that's what identical means. Basically, everything is the same between these two charges, magnitude and the signs. Okay, let's move on. And then point P, right? Notice that point P, it's not a charge, it's just a point. Distance away from these two things, these two identical point charges. So we only have 2 point charges in this scenario. And this one is just a point. It's not a charge. People make that mistake. It's not a charge, it's just a point. Likely it's a reference point by which we will measure the magnitude of maybe the electric field produced by either X or Y, depends. And then it's to the right of these charges, or to the right of charge Y, right? It's 3 millimeters away. And then we are told that the net electric field at point P, notice now it's electric field. It can be electric field or it can be electrostatic force. Be very careful when you read. Okay, so in this case it's electric field, and we know that electric field at a certain point is given by this formula right here, or E is simply F over Q. Depends on the scenario. You can use either formula, right? That's one thing you must note. And then we are told that it is this one. Remember, the net electric field at point P, it means we evaluate the electric field produced by X when we are looking at it from point P, and then we evaluate the electric field produced by Y at point P, right? And then we add these two together to find the net electric field at point P. That's why it's important to read carefully. Great. So now let's get to answering problems. We have broken down the question at this point. Okay, so we are asked to define the term electric field at a point. Like I said before, always make sure that before an exam you memorize your definitions. It's a free, I think it's 13%, right? The whole paper. So imagine just a free 13%. Now check this. We have, remember, the definition of electric field at a point says it's just the electric force experienced, or the electrostatic force experienced per unit positive charge placed at that point. You just need to memorize that. In formula or mathematically, it's given like this: E is equals to F over Q, right? But let's state it in words. So the electrostatic force experienced per unit positive test charge placed at that point. That's how you would define electric field at a point. And then we said mathematically it can be given as, let me just say, okay, mathematically it can be given as E, the electric field at a point, is F over Q. Right, so let's go to 8.2. Okay, so in 8.2 we are asked, are the charges negative or are they positive? We're not asked to provide a reason, likely because it will take forever to explain it, but here's the logic. It won't take forever, really. So point P is just a point, right? We don't care about it. And we are told that these two are identical. It means same magnitude, same sign, right? So if the net electric field point at the net electric field at point P is to the left, what does that mean? Remember, whenever we decide the direction of an electric field, we ask ourselves, if I put a positive test charge here at P, would it be attracted or would it be repelled? So would it go left or would it go right? Now in this case, since these are identical, we can just use this logic and say, well, if there was a positive test charge at point P and these two are identical, which means the sign is also the same, so I don't have to consider each one of them individually, I can then say, well, since it's to the left, it means these two must be negative. Because if I put a positive test charge here, it will be attracted to a negative charge, right? So these two must be negative because of that reason. However, if they were positive, the net electric field at point P would have been to the right. So since they are negative, and we are convinced that they are negative, therefore the net electric field at point P is to the left. So we know now that they are negative. That's one way to look at it. Another way to look at it is, you know that for a negative test charge, for a negative point charge, field lines are usually going inwards towards the charge, right? Forgive my sketch. But for a positive one, okay, let's finish this one. For a positive one, on the other hand, they are usually going outwards, you see. So it makes sense for us to say these charges, which is X and Y, are negative because their electric field or their net electric field is to the left, which is inwards when we look at this diagram. Okay, that's how we would answer this question. Now let's go to 8.3. We are asked to draw the resultant electric field pattern for charges X and Y. Since they are identical, it will be a pattern of repulsion. And we have already decided that they are negative, so we should also indicate that in the diagram. Right, so we have these two. They are both negative. Right, then now we draw our field lines. There will be a field line here. There will be another. Okay, my bad. Right, there will be that field line there. Right, and then they'll keep just going out like that. Okay, my field lines look ugly. Right, these are our field lines. Notice that they are symmetric. By that I mean if you slice it here, you'll see the same thing on top and above there. Right, and then they don't touch each other and they don't cross the circle. So if you have the circle, when you draw the line, it shouldn't cross the circle like this, and the lines shouldn't cross each other. You shouldn't have something like this or something like this. There's no need for that. All right, and then the arrows, since these are negative, the arrows should be pointing away from the charge itself, or from the circle. Away, 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 away. Everything pointing away. See, so this is how you would draw the electric field pattern for the net the resultant electric field pattern for charges X and Y. Okay, so let's go to 8.4. We are asked to find the magnitude of the charge X. Right, so even if we find the magnitude for the charge Y, it will be the same as charge X. So remember, at the start of the problem, we were told the net electric field at point P. So that what that means is in it would be E1 plus E2, or EX plus EY. Let me call it EX and EY for simplicity. EX and EY. What I mean by EX is the electric field at point P due to X, and the electric field at point P due to Y. So EX is that and EY is that respectively. So that's how you would do it. And then we would start substituting our answers. So our values. So for EX, we would have K, let's say maybe QX over R squared plus K QY over R squared, and then this is init. But remember, we are asked to find QX, not QY. So the magnitude of the charge X, we are told, actually let me say we're told that QX is the same as QY. So therefore I can change QY to QX and then continue solving. So what that translates to is init is simply QX over R squared. Then from here, it's easy to see that actually, let me not substitute yet so that I don't confuse you. Let me leave it as QY, right? And then let me do it like this. I'll substitute after. So let's just sub in the values for now. We have 9 times 10 to the power 9 QX, right? Over, how far is X from P? Because we're looking at it from P. It's 5 millimeters. 5 millimeters is the same as 0.005 squared, or meters. Remember, we work with meters and not millimeters. How far is Y from P? We come here, we check. It is 3 millimeters. That's 0.003 meters, sorry. And then at this point, this is now where we can substitute QX with QY with QX. Right. So at this point, we can take this and now we can have QX here as well. So this yellow is fine. This I did here. Right, do you get it? So now we do that, and then we can also substitute our net force, net electric field that we were given, which is 5.44 times 10 to the power 6, 5. And then start solving. So let's simplify everything. You can just punch in your calculator. So I get 1.36 times 10 to the power 15 qx. Right, well, let me put it in brackets for you. Then 5.44. From here we can simply divide both sides by this value 1.36. Right, so we can have here, we divide by 1.36, we divide by 1.36 here. So we simply do, oh no, one point 1.36. Right, and then we can find our qx finally. When I punch in my calculator, I get that qx is 4 times 10 to the power minus 9. Remember, they only asked for the magnitude and not the sign. So qx is 4 times 10 to the power minus 9. But we know in actual fact that it should be minus 4 nanocoulombs, based on what we've been talking about, or how we answered the previous question. So this is how you would find qx. It's 4 times 10 to the power minus 9 coulombs. All right, so let us go to 8.5. 8.5. So charge has no direction, so you don't have to worry about that. All right, so charge y is now replaced by an identical oppositely charged point charge. So if charge y was negative, which it was, it is now replaced by a positive charge. So what that means is now we will have non-identical charges, or they will have the same magnitude but opposite signs. So they are somewhat still identical, but now the signs are not the same. And then we are being asked, how will the magnitude of the net electric field at point P be affected? Increase, decrease, or will it remain the same? So here the answer is quite easy to get to. If you think about it, if these charges are the same, when we do the net charge, or the net electric field, we simply add them together and they will add each other up, giving us a bigger number. But now when it's opposite charges, they will subtract each other, meaning the final answer that we'll get will be lower than the one that we got when they were still identical. So opposite charges will give you a lesser net electric field at a point compared to like charges that are still identical. You get it? So that's how it would work. So the reason here, we simply say decrease, right? Because I like because now the fields from x and y, they will now act in opposite directions, and therefore they will subtract, leading to a lower net electric field. So that is how we would answer this particular question. They will decrease. The net electric field will decrease because the fields from x and y are now acting in opposite directions, and as a result they will subtract one another, leading to an obviously lower sum than before. All right, so that's it for this video. I will catch you on the next one.